What's up everybody, welcome to Totslam, the slum of tutorials, and Bieber's here with you. In this video I'm gonna show you the expectation maximization algorithm. This algorithm, which is called the EM algorithm for short, is applied mainly in machine learning applications. Actually, since you've looked for this video, so you're most probably knowing what it's used for. Whatever this thing that made you look for this video in the first place. You can find a really cool tutorial on the web, this paper by Chong-Bi-Do, which is titled "What is the Expectation Maximization Algorithm?" and it's written by Chong-Bi-Do and Bazzoglu. Actually, I'll be going through the example mentioned in this tutorial here. Okay, let's begin first by maximization, because we actually do maximization every time and we don't even notice it. In this example, this coin is tossed and the outcome is either a head or a tail. We all know this is the job of coins in mathematics, produce heads and tails. I guess this is the only thing that mathematicians need for money. Anyway, the bias of the coin is theta towards heads, which means for one toss it produces a head with probability theta, which is between 0 and 1. Now we toss the coin 10 times, and based on the outcomes we deduce theta. For this specific example, we have the following outcome: 3 heads. So the best value for the bias we estimate is 3 divided by 10, because these are 3 heads out of 10 tosses. Let's reflect about this problem together, because it seems straightforward in some sense, that you're just dividing the number of heads divided by the total number of the tosses of the trials you did. But there is something hidden here. The bias in which the coin is made by, due to its physical attributes like weight distribution and blah blah blah, this bias might have been something else different. Actually, you may do another 20 tosses, then end up calculating the bias this way, and you find a value like 0.2 or 0.4 instead of 0.3. We might not be getting the true value of the bias out of 10 tosses only, but this is just the way we do it, because this is the most likely value from this outcome here, and most likely is the key word in this situation. So why 0.3 specifically? Why it is the most likely value? That's not because we just take this for granted, dividing the number of heads by the total number of tosses. It's because this value maximizes the probability of the outcome, which is the joint probability of the heads and tails together. The probability of the outcome is this formula here, which we're gonna call Q of theta, and we're gonna maximize Q over the different values of theta. Then we can find out that Q of theta is maximum when theta is equal to 0.3, 3 divided by 10. You can actually find maximize Q by deriving, taking the derivative of Q with respect to theta and making it equal to 0, and then you find the value of theta. And you will end up actually with theta equal to 0.3. So it's not something taken for granted. Now that we have talked about maximization, let's move to the EM algorithm overview. The EM algorithm tries to deduce unknown parameters in a problem like the bias in the example we have mentioned, but with an example in which the information we have is incomplete. And that's why comes the expectation part at the beginning. The expectation part is expected to expect. I shouldn't confuse you. The expectation part, its role is expecting what fills this incomplete information. The algorithm performs expectation followed by maximization in an iterative fashion, from which each iteration gets us better values compared to the previous iteration. So, what is expecting incomplete information? Here is an expectation example. We have two coins, A and B. This time, we know the values of their biases, theta A and theta B. One of these coins have been tossed 10 times, and this is a corresponding outcome. This time, we know the biases of the coins, but we don't know which of the coins has been tossed. But we are gonna know. We're gonna estimate that based on what? We have nothing in our hands except the outcome and also the biases of the coins. So we're gonna base our assumption which coin have been tossed on those two things that we know. In expectation, we are required to take two steps. First, fill the missed information that we don't have. In this case, the missed information is which coin have been tossed to give this outcome. And we're gonna represent this information by a probability density function. Actually, in this case, it is a probability mass function because we have just two coins. We don't have some kind of a continuous spectrum of coins that we're gonna deduce a probability density function over. So we have only probability of coin A or probability of coin B. And after we deduce this probability, estimate these probabilities, we come up with the Q function. I'm gonna call it Q, you can call it anything, but anyway, most of us call it Q. It's a function of the biases, and it is very much like the Q function that we have that I've showed you in the maximization example, but in this case it is a log likelihood function of this outcome for using coin A and coin B, and then we apply expectation over those two log likelihood functions over the probability mass function that we have just deduced in the first step. Actually, it's the most important step, this one, deducing the Q function. If you can't understand it now, actually, I'm coming to it in 2 minutes. I promise you're gonna understand it. So, how do we get the probability mass function? The probability of A and probability of B. First, we do that by calculating the probability of the outcome given which coin being used, whether it is A or B. And this is very easy to write. We just calculate our joint probability. In this case, this is the probability of heads, 4 heads. The outcome is 4 heads and 6 tails. And this is a probability of 6 tails, and we come up with this number. These two probabilities, for example, this first one, it is kind of directly proportional to the probability of coin A being used. And the same thing for this one. It is directly proportional to the probability of coin B being used. So from here we can just get the probability of using coin A or using coin B. The point is that we need those two quantities to add to 1. And here it is. These two quantities add to 1. And this is the same ratio. If you divide this by probability of A by probability of B, you're gonna get the same ratio if you divide this by that. Hence now we fill in the probability of A as well as the probability of B. You can see here that the probability of A is obviously larger. You could have deduced that right from the beginning because theta A was 0.3 and the outcome was 4 heads out of 10, which is a little bit close. While on the other hand, theta B was 0.6, which would have been close if the outcome was like 6 heads out of 10. So the outcome was kind of shouting at us, I come from coin A. And that's why the probability of this outcome being coming from A is higher than the probability of using coin B. Now it's time to do something with this probability mass function that we have just come up with. Here comes this equation. which is the most important equation, most important thing in this whole algorithm. And when you are able to wrap your head around this, then you are done with everything. It looks a little bit cumbersome, but it is really very easy, very simple to be broken down. Actually, in more sophisticated example, you're gonna see this equation that might take a whole page actually to be written, but it's just very easy to be broken down. We're gonna look at it now. First, we write the probability of the outcome for both coins, A and B. You see this equation, this formula. This is the same like this one. It is the probability of outcome given that the coin is A, and this one the probability of the outcome given that the coin is B. Then we apply log function for both those probabilities, so that it becomes the log likelihood. After that, we average. It's like weighting both likelihoods for their probabilities of occurrence. So this one gonna multiplied by probability of A, and this one gonna multiplied by probability of B. After that, when you add them together, this is the expectation over the probability mass function of using coin A or using coin B. And finally, we get our Q function that is gonna be maximized in the next step. Now let's put E expectation and M maximization together in one big example. You're looking now at a part of the paper that I mentioned in the beginning of this video. So allow me to plagiarize it. We say here in my country that confession is the master of evidences. So I don't know if I am considered to be plagiarizing, if I'm admitting I'm plagiarizing and mentioning the text and the author I plagiarized from. I really don't know. We become philosophical when we are high, I guess. Anyway, I think I'm just overly concerned about it. I just shouldn't be doing something wrong. So anyway, in this example, we are having two coins, A and B, and we are taking one of them, tossing it for 10 times, and we repeat this process for another 4 times, for a total 5 times here. And this is using either coins A or B, and we don't know which one we are tossing for each one of the 5 times here. Our final goal is to get the biases of the coins, the biases that we don't know. And you remember we were getting the biases from the maximization step. All what we have here, just this raw set of data in front of us. These are just a stream of heads and tails, and we don't know which outcome belongs to which coin. So first, we propose a value for the coin's biases. Any value, just here, these 0.6 and 0.5, any value. Just to begin with, there is nothing special about these particular values here, 0.6 and 0.5. Everything is gonna be fine from here, just something to begin with. So, based on this value here, we get, and of course the outcomes, we get the probability mass functions that we talked about. These are the probabilities of having used which coin to get the corresponding outcome. After that, we get Q. That is the expectation of the log likelihoods, as I told you, of the outcomes. This Q function actually that we're gonna write for all those 5 outcomes together. It's gonna be a very big Q function here. Remember how we come up with our Q in the previous example? We come up with 5 of those and just add them together, and everyone is multiplied with its corresponding probability, and now we get this one big Q. We just add them together because log probabilities add, because that's the point. Actually, it chose to make it a log likelihood functions. We don't need to multiply them, just add them, and they are simpler to deal with. After we get this Q function, we maximize it. In this paper, the author just multiplied the counts of the heads and tails by the corresponding probabilities. For instance, in this first line here, we have 5 heads and 5 tails. So he multiplied 5 heads by 0.45, which is the probability that coin A have been used. And he come up with 2.2 heads and 2.2 tails, because it's also 5 tails, multiplied by the same quantity, 0.45. For this one here, we have 9 heads. He multiplied 9 heads by 0.8 to get this number, 7.2. And also he multiplied 1 tail with 0.8 and to get this number, 0.8. He did the same thing for coin B, but multiplying with the probabilities of using coin B. Then he added the heads and the tails in order to divide the number of heads by the total number of tosses. Here it's gonna be 21.3 plus 8.6. After doing that division, he gets the bias for A and the bias for B. Usually the author did that, and this is like the first maximization example when I could have divided the number of heads 3 by the total number of tosses, and it is the same thing as maximizing the Q function and also getting the same number. So actually, usually in real examples, big examples, not like coin tosses and such stuff, we use calculus to get the parameters theta by maximizing the Q, and you will end up doing the same thing. Actually, if you picture it in your head, the powers, which are the repetitions of heads and tails, these powers will get out of the log function to be multiplied by these probabilities, 0.45 and 0.55, all these probabilities, which will then get added together until you reach the same result here. From those thetas here, the 0.71 and the 0.58, we can do expectation again. We get back to the first step. Hopefully, after entering this loop, we get better values the next time. And we do that each step till we stop when we see we are not getting much change anymore. Now that we are done with the EM algorithm, I really hope I helped you understand it. If there are any questions, please leave them in the comments, and don't forget to like this video and subscribe for hopefully more new tutorials. Thank you.